away. That goes away, and this goes away. What is 2 over 3 factorial? 3 factorial is 6. 3 times 2, fine. Good harmony there. Same answer. Perfect. 2 over 6 is 1/3. Yeah, A is 1, the point. Yeah, exactly. So is this centered at 0? No, it's centered at 1. Sometimes you're going to need to do that for investigative purposes, and sometimes you're going to have to do it, because sometimes the function isn't defined at 0. So on this one, we just need to make sure we do the exact same work, but remember, we're not centered at 0. What are we centered at? 1, exactly. So what's that first thing we're always really going to do on these? Yeah, there you go. Someone first write it as 1 plus x to the 1/2. So what's f prime of x going to be? Yeah, well, there you go. Hey, luckily, do we have to use the chain rule in any appreciable manner? We're technically using it. What are we kicking out? We're kicking out a 1. We're going to write that in. And then f double prime is going to be negative 1/4, 1 plus x to the negative 3/2. F3, what's that going to be? Yeah, it's going to be 3/8, 1 plus x to the negative 5/2. Do I go any further? Why not? It's telling us to stop there. It's telling us to. What do we plug in now? Not 0, we plug in 1. Luckily, is this a rather nice thing to plug in? Yeah, you get root 2. F prime of 1, what's that going to be? 1/2 of root 2 to the negative 1. I'm going to write it like this so I can fit it on a line. Is that okay? What's the next one going to be if I write it the same way? Root 2 to the what power? Negative 3. The bottom of that fractional power, the half, makes it a square root. So I'm just writing it as root 2 like that, just so you can see it. Some a little bit nicer. So what's that next one going to be, Emily? Correct. Do we now have all the ingredients? Yes. Let's put all the ingredients together. Don't try to simplify yet. Let's put all the ingredients together, see what we get, and then after we see what we get, then we can decide if we want to simplify or not. So when we do this, what's the first term going to be? F of what? F of 1, exactly. And we figured out what f of 1 is. What is that? Root 2. The next one is going to be this term right here, all over what? 1 factorial x. What's the next term going to be, Umi? Which is? Nope, that we just used that one. So it's going to be this one, root 2 to the what? Over. Times. Yeah. Oh, you caught it. Exactly. What are we actually centered around? 1. So we're not quite right here, right? What do we need to actually put instead of x? Yeah, so it's going to be x minus. Oh, there it is. And this one's not x squared. What is it? Yeah. And then what's the next term going to be? 3/8 times root 2 to the negative 5 all over what? 3 factorial times to the 3rd. Exactly. Now here's the thing. Is that the most simplified form? No, but have you glued it all together? At this point, the only thing you need to do is some algebra. And if you check the answer book, they rewrite it in a pretty nice way. Anybody want to guess what number they factor out? They factor out a root 2, because when they do that, all the even powers of root 2 turn into powers of 2, right? All the odd ones then turn into powers. It makes it so you get really nice things here. Because look, all of these are odd powers, right? See this? Odd. By factoring out a root 2, you get an even, and therefore it turns into powers of 2. So you have root 2 times something with no root radicals in it. The point is, sometimes when you look up the answer key, which you might have already because I gave you a present in your handouts, it cleans it, it makes it look nicer. What's interesting is that you can think about it, I like thinking about like what does nicer mean, and sometimes it's going to be frustrating because you will look this one up in the back of the book and you might be like, it's not the same, and it actually is. The work on this one, it shows you what they do. Are you okay? E to the x is a really nice thing, and we're doing it around 0 as well. So in this case, for this function e to the x, f of 0 does equal f prime of 0 equals f double prime of 0, right? In fact, equals fn of 0, which is all going to be what? No. 1. When you plug in 0 for x into e to the x, what do you get? 1. So it's fine. You're really excited. It's 0! So when you construct your Taylor polynomial, this one comes out kind of nice. What's the first term? 1 plus 1 over 1 factorial x to the 1 plus 1 over 2 factorial x to the 2 plus 1 over 3 factorial x to the 3 all the way up to what? 1 over n factorial x to the n. Is it written like that generally? No. Usually you see it written as what? 1 plus x over 2 factorial plus x cubed over, thank you, 3 factorial plus all the way up to x to the n over n factorial. Is that about as nice as it gets with regard to Taylor polynomials? Yeah, it really doesn't get nicer than that. We actually saw something that looked kind of like that yesterday. What did we see that looked kind of like that yesterday? When we did sine x, right? Sine, it was just the odd ones, remember? It was just the odd, and it was alternating sine a little bit. But is it not radically different, it's pieces of it, right? Okay. So the general term that you see is written out like this right here. You see this general formula, not general formula, but you see this general formula for a Taylor polynomial of degree n approximating f of x for x near 0. All of it comes down to the central idea yesterday, which was there was one thing I said. If there was one thing that you needed to remember, what was it? Do you remember? This. What is Cn? Raise your hand if you know what Cn is. Yesterday I circled it and said if you remember one thing, remember this. Remember what Cn is? It's the coefficient of x to the n. What is the coefficient of x to the n? Emily, what is it? It's f. It's a specific f. What? F of all over n factorial. I circled this and said, if anything, remember this. Because that is the coefficient when you're centering the Taylor polynomial around 0. Look at all those terms. You see all those crazy things like, man, I got to remember this whole thing. You don't remember all of the letters. You remember the sentence. And the sentence is entirely built around this right here. What goes right here? X to the n. That makes your term. Now, are you always centered around 0? No, you're centered around a sometimes, but it doesn't really change much. If you remember this, you're 90% of the way there. Taylor polynomials are entirely built around that phrase right there. So let's say we wanted to construct this Taylor polynomial, a Taylor polynomial for this one. 1 over 1 minus x. Hey, we're around 0 even. Is that nice? It is. Again, what's that first thing you need to do when you're constructing a Taylor polynomial? Find the thingies. I like that. Find the thingies. F of x is 1, is it plus? No, it's 1 minus. 1 minus x to the negative 1. So what do you have to make a list of first? The what? The derivatives. Now, Umi, how far do I need to go on this? Ah, perfect. You have to go until you see a pattern. Hopefully not just sitting there for the rest of your life writing out this infinitely long list of like, I'm stuck. I mean, that does happen in the Never-Ending Story, and they end up breaking out of it because Bastian finally says, like, the name of the childlike princess, empress, and therefore, like, recreate. You don't read these guys. I know, it's good. Read the book. The movie's only the first third of the book. What's the next one? Never-Ending Story. Originally written in German. Fantastic, fantastic book. Turned into one of the best 80s movies of all time. What's the next derivative? 2, 1 minus x to the times equals 2 times 1 minus x to the negative 3. Well, what's f triple prime going to be? Negative. I'm going to write it like this instead to help you guys out. Because what did Umi say? We have to do this until we see a what? So what's it gonna? Oh, it's to the -4. Sorry, see, you're absolutely right. The -4 up there equals. I'll give you a hint. So, oh, look at that. Oh. Nice. Oh, do we see a pattern? Oh, yeah. Am I like hating on 4 here today or something? Do you see a pattern yet? You're welcome. So, what's Fn going to be on this one? Anybody? What's it going to be? N factorial times 1 minus to the n plus 1. Right. Hey, we have the general term now. Okay, we're constructing the Taylor polynomial around 0. I think it's at around 0, right? Yeah. So what do we plug into each of these? We plug in 0. And look what happens. This one, f of 0, is going to be 1. What's f prime of 1 going to be? Oh, why am I plugging in 1? I don't know. We're going to do that later. What's that going to be? What is it? 1. What's f double prime of 0 going to be? 2 factorial. What's f triple prime going to be? Oh, so we do this, so we think that fn of 0 is going to be n factorial. That's kind of cool, but a really neat thing happens when we plug this into the formula for jet. What's going to happen?
It cancels with the thingy.
Oh, it cancels with the thingy! Nice. So you're absolutely right. It does cancel with the thingy. I speak teenager math. It's good. What's the first term? 1 plus, well, it's going to be 1 factorial over 1 times x, and then the next term is going to be what? 2 factorial over 2 factorial x squared, plus 3 factorial over 3 factorial x cubed, all the way up to n factorial over n factorial x to the n. All the factorials on the top came from the derivatives evaluated at 0. Where did the bottoms come from? The formula that we have, right? That expression, the general expression of the Taylor polynomial. Oh, what cancels? A whole lot of stuff, right? Yay, they go away. So what are you left with? 1 plus, you end up with this thing, which is kind of cool, which is another way of writing what? 1 over 1 minus x. That's the original function that we did. And here you've actually seen this before, and you can easily prove that this is true. If you cross multiply this thing, put these all over 1, right? Put this whole thing over 1. Put a big bar here and put it over 1. If you cross multiply, you get 1 times all of this, right? And then you multiply negative x times all of this, and what happens? Tons of things cancel, right? Another thing is, have you seen something that looks a lot like this? What does this look like? What does that look like? Something over something minus x. Oh, what kind of series is this? It's a geometric series. What's the sum of a geometric series? The first number over 1 minus. It came out again. There are multiple ways to show the same thing is true. Kind of cool, huh? Right? Oh, kind of neat. What happens if x is less? What happens if the absolute value of x is less than 1? It converges nicely, right? Oh, but does this always converge? No, it doesn't. If x is 1 or greater, right? Oh, it all comes together. Sweet. Excellent. It's not around 0. Could it be around 0? This is just the general case where it is centered somewhere else. Now, centering at 0 is nice because we like plugging in 0 and just go away. It's nice to plug in. But are we always able to center around 0? Look at the bottom. Construct the Taylor polynomial with degree 4, approximating function f of x to 1. Why don't we do 1 instead of 0? It doesn't exist. Natural log does not exist at 0. Natural log is actually pretty cool because, is it as cool as e to the x? I don't think so. Yeah, we're making, I love how, do you like how we're making like judgment calls on things that are like the antithesis of judgeable? You know? What's the most morally ambiguous subject, theoretically? Here we are. Welcome to moral ambiguity. Numbers exist. Natural log is a function. That's very nice.
Did humans invent math, or did we discover
Did Columbus discover America? It all depends on who's writing the history.
But like, did math exist before we started thinking?
What I'm getting to is the derivative is not perfectly nice, but it's still pretty nice on it. What's the derivative of ln x? What is it? Wait, what did you just get stuck on there, Umi? Is that okay? Is that okay? Cade's like, can we stay on topic, please? What's the second derivative going to be? 2 f triple prime and f4. Now, did this ask us to find the general form for this? No, it just asked us to find the degree 4. So do we really care about establishing a pattern? No. Now, we're centering it around 1, and guess what? When we plug in 1 into all of these things, what happens? What's ln of 1? 0. F prime of 1, what's that? 1. F double prime. F triple prime, written like Umi wants me to write, 2. F4 of x, what's that? Negative 6. Do we now have the coefficients? Can we build the coefficients? These aren't the coefficients. These are the numerators to the coefficients. What's the first term? 0 plus 1 over 1 factorial x plus... good catch. We're not centered at x anymore. Look at that. We did it earlier this time. Excellent. What's the next one? What's the next one? Negative 1 over... x minus 1 squared plus what? You got it. Times. And then the last one's going to be, it's over what factorial? 4? Yeah, just increments. X minus 1. So these things, they look super nasty, but oh man, what am I doing on 4 today? It's incredible. You've done some weird hypnosis thing, right? Where I'm actually like secretly blacking out dancing for a little while and all the 4s turns into 3s. What? You've never gone to a hypnotist before? Never seen that happen? Okay. Do any of these terms go away because there's zeros in front of them? No. I mean, the first one, true, yeah. But all the terms are there. So if you clean this up, you end up with x minus 1 minus what? X minus 1 squared over 2. Well, I'm going to clean it up. I'm going to get rid of the 2 factorial. X minus 1 cubed over 3 minus x minus 1. Look at that. I wrote a 4 over what? It's 4, right? Cool. So we've now written the Taylor polynomial of degree 4 approximating the function f of x equal ln x for x near 1 to the 4th power. Kind of cool. Now, that's centered at 1 because can we center it at 0? No. Things break. Things break. Yeah, in calculus, there are some things you have to memorize. Here are 3 of them. It looks terrible, but they're really straightforward. This is how I remember them. What's e to the x? The simplest one, because everything is there and it's all positive. 1, x squared, x cubed, x to the 4th, they're all positive. And what are all the denominators? 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial. That's what I remember. E is the easy one. Easy. The next one I always remember, cosine is even. And that's all our even and even. Even. Just remember cosine is even. The thing about cosine and sine, they both do the same alternation, minus, plus, but they start different places. So if you start at the even, you only see even powers of x, and you only see even denominator that's factorialized. So look what you have here, 1 minus x squared plus minus plus 2, 4, 6, 8, 2, 4, 6, 8. So if you get cosine, should you always go with sine? Sine is just the odd ones, alternating the same way. Positive, negative, positive, negative, positive, negative. You need to remember these because you're not going to have to prove them every time. You don't need to be able to prove them every time you use them. It'd be nice if you could, but do you have enough time to prove this every time you want to use it? You need to prove the quadratic formula every time you want to use the quadratic formula? No, it's the same exact thing. You're going to use these so many times, it's going to be hopefully relatively straightforward. Now, these are the general terms for them. Which one is this? Which one is that? That's E, yeah. Which one's this? Is that cosine or sine? It's cosine, because it's that 2k. 2k generates what type of number? Even. Exactly. Go ahead, on the board. Everything else you've seen before. What's the one change from 10.1? We're now 10.2. And we went from one thing to the next. What's the next thing we went to? Instead of calling it a Taylor polynomial, we're now calling it a Taylor series. Ooh, why is it called a Taylor series all of a sudden? We were adding it before, but now how far do they go? All the way! Exactly. They go all the way. Taylor series and Taylor polynomials are going forever. That's it. That's it. That's all they are. Have we seen this term before? Yeah. Did I tell you that was the most important part? Yeah. Know that coefficient and everything else is a lot easier. Oh, what's the only change from here to here? Yeah, it's actually x minus 0 right there. That's all it is, right? This is just the case where it's centered around 0. Taylor polynomial, we like these things centered around 0. Nice. Okay, so we already constructed this one right here. We constructed that one. And this is what we got. Do you remember how we got that formula right there? Does that look familiar? Remember this? 2, 3, 4 goes all the way up. Here's the generalized term right here. The black function right here, this is the black one right here, that is ln x. That is ln x. The blue functions are p5, 6, 7, 8. Those are the Taylor polynomials of degree 5, 6, 7, and 8. As the Taylor polynomial gets higher in degree, it becomes a better estimate. So what happens to this blue? If you zoomed in, they're getting closer and closer to ln x. But they're only getting closer and closer to ln x between 0 and 2, because 0 and 2 is the what? Is the interval of convergence. And it kind of makes sense when you look at the picture, because look at the degrees here, P7, P8, P6, P5. When it's odd, it's going up, and when it's even, it's going down. But more so, look what happens. Here's P6, here's P8. Is that moving towards or away from ln x? It's moving away. So it's doing the definition of divergence. It's moving away here. So gravity is working in our favor here. But what's happening outside? It's divergent. Exactly. And then over here, it doesn't matter because the function itself, ln x, isn't defined outside. So visually, does that kind of make sense? So when we use, if we were to use this equivalency, we can only use it when x is between 0 and 2. That kind of makes sense? We'd also have to test yes, Emily, what's the question? Okay, we calculated it, calculated the Taylor for ln x, right? Is that almost what we're trying to find the Taylor series for? Almost? What's the only difference? Instead of ln x, we're doing ln x plus 1. You are going to be able to build Taylor series with existing Taylor series by just doing substitutions into existing Taylor series. So for this one, you have ln x is equal to that thing, right? But instead of ln x, guess what we get to write? Instead of x, what are you going to plug in there? Take a guess. You're just going to be able to plug in x plus 1. You get to take x plus 1 here. So, and actually, look what happens. Oh, you like it as 1 plus x, right? So if I plug in x plus 1, what do I end up with, everybody? X minus what? Plus minus dot 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 negative 1 to the n minus 1 times, instead of x minus 1, what do I have now? To the n over. Hey, is that what you guys figured out all by yourself already? Kinda, some of you maybe, kind of look over there, you kind of see it. Take a look. Look, bottom left right there. Someone did it in blue. The point is, could you do it all out by hand? Yes. But is there a shortcut? Yeah, there's a substitution. You can actually just substitute in 4x. You know, for example, e to the x is equal to that thing. What happens if I said e to the 7x? Just plug in 7x for x. Do you know sine x? Yeah, what about sine of 6x plus 9? Plug in 6x plus 9 for x. I think then you can build new ones. Okay, kids, I think that is it.